All right, ladies and gentlemen, thank you for joining me digitally for today's class. We're going to start chapter 7. And remember to do your homework for section 7.1. I'm going to collect it and grade it and roll that into your participation grade. Below here on this slide is the amended homework for section 7.1. If you printed out the homework sheet at the beginning of the semester, these problems are slightly different. I took off a couple of problems, so just make sure you're not doing those extra problems. The sheet on Blackboard is correct now as well with these problems. All right, so we're going to start section 7.1, which is on estimating mu when sigma is known. So an estimator is a sample statistic that estimates a population parameter. Remember, we are usually interested in the whole population, but we settle for a sample because getting a hold of the whole population is very difficult. We will have two types of estimators, point estimates and interval estimates. And point estimates you are familiar with. We have been doing these all semester long. For example, if we are interested in the mean or the average, the population mean, we use the symbol mu. We usually can't get a hold of the whole population to find its mean, so we settle for the point estimate of x bar. That's our sample mean. If we are interested in the population standard deviation, we used the symbol sigma for that. And if we can't get a hold of the population, we settle for the point estimate of lowercase s. And sigma and s, if you'll recall, had some pretty gnarly formulas that you had to use on your first exam. And we will review those a little bit later in the chapter. And then our most recent one we've learned about is the proportion. If we're interested in the population proportion, we use a lowercase p. And then our point estimate that we learned about in chapter 6 for the population proportion is the sample proportion, and we use p with a little hat on it, p hat. Okay, so just as a quick review of sample means and sample proportions, we'll do a little example here. Example 7.1.1, sample of 100 apples is taken from a harvest of over 200,000 apples. The sample weighs 11,200 grams. Find a point estimate for the mean apple weight for the entire harvest. Okay, so what we're really interested in is the mean apple weight for the entire harvest, and that would be mu. So, but we only have a sample of 100 of the apples, so we're going to find the point estimate, and that would be x bar. Okay, so we're just going to find the average weight of the sample, and they already added up all of the apple weights for us. That's that 11,200 grams. And we'll divide that by the 100 apples in the sample. So our sample mean is 112 grams. Okay, so that is our best guess for what the average weight of the entire harvest is, 112 grams. All right, in part B, they tell us that 18 of the apples in the sample are Honeycrisp apples. Find a point estimate for the proportion of the apples that are Honeycrisp apples. Okay, so again, the proportion of the harvest, the entire harvest that are Honeycrisp apples would be the population proportion. We would use a lowercase p for that, but we're finding a point estimate for that. So that's going to be p hat. So we just want to find the proportion of our sample that is Honeycrisp apples. All right, and there are 18 out of 100, so that gives us 0.18, or 18% of the sample is Honeycrisp, so we would guess that 18% of the entire harvest is Honeycrisp apples. All right, so that's just calculating point estimates, but we want to do better than point estimates. So we move on to interval estimates. All right, so instead of just saying the mean weight of an apple is probably 112 grams, maybe we might give an interval estimate. So this interval estimate would say, okay, 112 grams is our best guess, but we're going to say that a good guess is that the average weight of an apple in this harvest is between 104 and 120 grams. So that's an interval estimate. Okay, and we call it a confidence interval because all of these intervals, we are going to attach a level of confidence to it. So maybe I might say that I'm 95% confident that the real mean weight of an apple in that harvest is between 104 and 120 grams. All right. So our general form for one of these confidence intervals is the point estimate plus or minus the margin of error. So for example, that interval estimate graphed on this page started with our point estimate of 112 grams. Okay, and it looks like the margin of error that was used for this interval was 8. So we did 112 plus 8 to get 120, 112 minus 8 to get 104. Okay, so the point estimate is pretty easy. That's just the sample mean in this case, but the margin of error is going to be the tricky bit to figure out. How do we figure out what that margin of error would be so that I'd be able to say I'm 95% confident or I'm 99% confident or however confident we want to be? So that margin of error is going to depend on two things. The first thing is how confident we want to be that our interval contains the actual parameter. Okay, we would really like our interval to contain the true population mean, all right, but how confident do we want to be? Okay, so we gave the interval 104 to 120, and I said maybe I might be 95% confident about that. So what if I wanted to be 99% confident? Maybe I would need to give a wider interval. So if you want to be more confident, you have to throw a wider net to make sure that you catch the true population mean. And you can never be 100% confident. I mean, if I wanted to be 100% confident that my interval contained the true population mean, I would probably have to say that I'm 100% confident that the mean apple weight is between 0 grams and 1,000,000 grams. So any interval that you could be 100% confident about would be completely useless. All right, so, but in general, the more confident that we want to be, the wider we have to make our interval. All right, the other thing that the margin of error is going to depend on is the sampling distribution, and that is what we learned about in part 2 of chapter 6, that x bar is distributed normally. We can calculate probabilities about x bar on the z table, and it followed this distribution, x bar minus mu divided by sigma over root n, and that would give us a z-score. All right, so focus on that numerator there, the difference between x bar and the true population mean, so our sample mean and our population mean. That is our margin of error. That's how far off our sample is from the true population mean. All right, so I'm going to solve for that using a little bit of algebra. So I'm going to multiply both sides of that z-score formula by sigma over root n. And I do that so I can get rid of them on the right-hand side and just have x bar minus mu left over. So on the right-hand side, I have x bar minus mu. And on the left-hand side, I just have z times sigma over root n. Okay. And so that guy right there is going to be our margin of error. Okay. So here's our formula for the confidence interval for mu. X bar, that's like our 112, plus or minus that margin of error that I just calculated on the previous page. All right, so the z comes with a little subscript of c, and the reason we put that there is because that z value is going to be associated with a particular value of confidence. So that z value is going to change if I want to be 95% confident or 97% confident or 99% confident. All right, so that's why it's got a little subscript. All right, if you had printed the slides out before, you have this version of the confidence interval. That means precisely the same thing as the one that I have written at the top. I think the one on the top is a little less confusing. So if you need to pause it and kind of scratch out that old formula on your slides and just replace it with this one, that's the one that I'm going to use going forward. Okay. All right, so this interval, this formula is only going to be valid under two conditions. And every time we use this formula, we're going to have to check these two conditions. Okay, so our first condition is going to be that sigma is known. So if you look at the formula up there, sigma is in the formula. So if we don't know the population standard deviation, we can't plug it in, so we can't use this formula. And we're going to talk later when we're back together again what to do if you don't know the population standard deviation. So today we're just going to talk about what to do when you know what sigma is. The second thing is you have to know that x bar is behaving normally. And in chapter 6, we learned that that will happen when the population itself is normal or when the sample size is big, bigger than or equal to 30. Okay, so we will either have to verify that the population is normal or check that we have a big sample size. All right. So pretty much that formula is going to be very much plug and chug. We're going to plug in x bar, sigma, and n. The tricky bit is figuring out that z value from the table. Okay, so we're going to calculate that z sub c from the normal table. And we have gone looking for z values on the normal table before. These were the problems where we would sort of search the guts of the table for a probability and then read it backwards to come up with the z value. Okay, so which probability are we going to be looking for when we're creating a confidence interval? All right, so let's say that I want to be 95% confident about my interval. All right. So what we're going to do is draw a z distribution and shade the middle bit, okay, kind of a symmetric middle portion of the z distribution. All right, so that middle bit is going to represent the probability that my interval actually contains the population mean. And if I'm 95% confident that my interval does, then that middle area is going to be 0.95. Okay? So if I'm 95% confident, that means that I'm 5% not confident. All right, so that non-confident area in this case is going to be 0.05. And we use the lowercase Greek letter alpha to represent that non-confident part, that area of being unsure. Okay, so that alpha, that 0.05, that's going to be the area that's stuck in the tails, those white unshaded tails. So that alpha has to be split in half between those two tails. They're sharing that alpha area. So half of the area, half of the alpha is going to be in the right tail, and half of it's going to be in the left tail. Okay, so in our case, when we're 95% confident, that's going to be 0.05 divided by 2, which is 0.025. So I've got 0.025 in the right tail and 0.025 in the left tail. All right, so if I'm going to go look in my z table to figure out the z value is that z-score right there. It's the boundary in between the shaded region and the right tail. So remember that our table only shades area to the left. Okay, so we got to figure out how much area is to the left of that z-score that we need for our formula. Okay, well, how much area is to the left of there? Well, it's got the shaded 95% area in the middle, and it's also got that tail that had the 0.025. So if I lump those together, 0.95 plus 0.025 gives you 0.975. So that's the area that we want to look for inside the table. Okay, so grab your z table and look on the positive side of the table. Okay, so here's as much of that table that I could fit on there. So I'm looking through on the positive side of the z table for 0.975. All right, and the closest thing that I can find to 0.975 is right there. That's going to be the middle of your table in one of the unshaded regions. I had to cut the bottom half of my table off. All right, so this is one of those rare cases where we actually find exactly what we're looking for. This is not very common. So then we read the table backwards. And so that's in the 1.9 row and the 0.06 column. So that number we're looking for is 1.96. All right, so I go back to my distribution and I find 1.96. And so that's how I find that z value in our formula. Like I said, this is the hard part, coming up with the z-scores for the formula. All right, but we have a little shortcut for it. Now we looked up on the positive side of the table because that's the number that we actually want. All right, but because the table's symmetric, look at this. If this tick mark is 1.96, then this one over here on the left-hand side is negative 1.96 because the table's symmetric about 0. Now go flip your table over and look on the negative side of the table, and we're going to look up negative 1.96. Okay, so there's negative 1.96, and look at the area in the table. That's the 0.025. That's that alpha over 2 area that was in the left tail. All right. So it would have been faster to go looking on the negative side of the table because we already knew what the left-hand area was from that negative tick mark. All right, so even though we really want positive 1.96, it's kind of easier to go looking for the negative number and then just lop off the negative sign. All right, so let's do a couple more of these to kind of get the hang of calculating z sub c. All right, so we're going to find that z sub c score for a 98% confidence interval. Okay, the process is the same as last time. You're going to draw your normal distribution and shade the middle bit. That middle bit is your confidence area, so that's 0.98. All right, then if we are 98% confident, then we are 2% not confident. So that gives us our alpha value of 0.02. That's our 2% uncertainty. All right, so half of that goes in the right tail. So we're going to take that 0.02 divided by 2, which gives us 0.01. So if we've got 0.01 in the right tail, we've got 0.01 in the left tail. All right, and again, this time I'm going to go look on the negative side of the table. I'm going to see if I can figure out what that negative z sub c is, because I already know the area to the left of it is 0.01. Okay, so we won't have to add up the other bits to go looking on the positive side. Okay, so I'm going to go to my table on the negative side looking for the closest thing I can find to 0.01. Okay, and the closest thing I find to 0.01 is right there, 0.0099. Okay, in that second shaded section of the table. All right, the other one that's closest to it would be 0.0102, but 0.0099 is closer. So we take that one, and that is the number negative 2.33. All right, so I found the negative number, negative 2.33, because it was easier to look up on the table. The number we actually want is the positive one, 2.33. Okay, so our z-score is 2.33. So we replace that c in the subscript, that z sub c, we replace it with our confidence level. So z.98, that's a little subscript, z sub 0.98 is equal to 2.33. All right. Okay, so part B, we're going to do another one. We're going to find z sub c for a 90% confidence interval. So if you feel like you got this, pause the video and see if you can find z sub 0.9 on your own and then check your answer. Or you can just watch along with me. All right, so I'm going to find a 90% confidence interval. Same process. We shade the middle bit. That's going to be our confidence area of 0.9. All right, so if we are 90% confident, we are 10% unsure. So that alpha is 0.1. Okay, so 0.1 gets divided by 2 because it's split between the two tails. 0.1 divided by 2 is 0.05. So I got 0.05 in the right tail, 0.05 in the left tail. And then we're going to go looking for our z value in the table. All right, so I'm looking on the negative side because I know the area to the left of the negative value is 0.05. So there's my negative side of my table. So I'm going to look for the closest thing I can find to 0.05. All right. And this is kind of the annoying one. I find 0.0505 and 0.0495. Okay, so those values are equidistant from the one I want, 0.05. All right, so if they're equidistant from the number that you want, we're going to take both of those numbers, negative 1.64, negative 1.65, and we're just going to average them. So do 1.64 plus 1.65 divided by 2, and you get negative 1.645. Okay. So that's our negative value, our boundary. And again, we really want the positive one, positive 1.645. All right, so that's our z.9 is 1.645. All right, so that would be the z value that we would plug in to our confidence interval formula. All right, so the next slide just has a table of values of z sub c for commonly used confidence levels. Most of the time we're either finding a 90%, 95%, or 99% confidence interval. So most of the time you can just look up the values in this table and you can certainly copy them onto your note card for the exam. But usually I pick a random value of confidence, like find the z sub c for a 72% confidence interval, just to test to make sure that you know how to find z sub c. But most of the word problems, I'll just use one of these typical values of confidence level. So from now, the two examples we're going to do now, we'll just kind of refer back to this table to find our z sub c value. All right. Okay, so now we're ready to go. This is our formula. When you're asked to find a confidence interval for mu, and you know sigma, and you know the population is normal, or you have a big sample size, then you're going to use this formula, and now we know how to find z sub c in the formula. All right, so let's just give it a try. Example 7.1.3 says, a publishing company has just published a new college textbook. Before the company decides the price at which to sell this textbook, it wants to know the average price of all such textbooks in the market. The research department at the company took a sample of 25 comparable textbooks and collected information on their prices. This information produces a mean price of $145 for this sample. It is known that the standard deviation of the prices of all such textbooks is $35, and the distribution of such prices is normal. Construct a 90% confidence interval for the mean price of all such college textbooks. Okay, so we're going to plug into our formula for a confidence interval. But before we do that, I'm just going to mine this giant paragraph for some numbers. And the hard part is going to be attaching the correct symbols to the information that they give you. Because once you do that, all you have to do is plug them into the formula and let your calculator do the work. Okay, so the first information they give us is that we've got a sample of 25. Okay, so our sample size is 25. That's going to be that lowercase n equals 25. So we're just going through the paragraph and taking notes. Okay, the next bit of information they give us is the mean price of $145. Now we have two different symbols for mean. We have mu and x bar. So you have to decide, is this a population mean or is it a sample mean? Okay, so they're referring to those 25 books. This information produces a mean price of $145 for this sample. So that's definitely a sample mean. And if they knew the population mean, mu, we wouldn't be making this confidence interval in the first place. We would just say what mu is. So that's definitely an x bar. X bar equals 145. Okay. The next thing they give us is this sort of weirdly omniscient statement. It is known that the standard deviation of all the prices of all such textbooks is $35. Okay, so that $35 is referring to all such textbooks. So that is a population standard deviation. That is going to be a sigma, not an S. That refers to the population, not the sample. All right, and that is a little bit of a weird statement. And it's kind of curious. You wonder, if we really know what the population standard deviation is, how is it that we cannot figure out what the population mean is? And so these are not really realistic situations, but it's kind of where we start off learning about confidence intervals. So we're just going to take what they tell us and run with it. Okay, so we have sigma equals 35. All right, so we have those three bits of information, and we're going to remember we want a 90% confidence interval. So I'm going to pick up those numbers and come over to my formula here. So here's my confidence interval for mu. We just figured out that n was 25, so I'm going to plug that in there. We read that x bar was 145 and that sigma was 35. All right, and again, that z sub c comes from the fact that they want us to be 90% confident about our interval. Okay, so we want to put z sub 0.9 there, and we just figured that one out. We got 1.645. Okay, so all we have to do is plug into our formula, but before I do that, we're going to double check to make sure that we satisfy the conditions for this formula. Okay, so the first thing we have to do is verify that sigma is known. Okay, and again, they told us that that standard deviation referred to all textbooks, so that was a sigma. Check. The other thing we need to know is that the original population is normally distributed, or that our sample size is bigger than or equal to 30. Well, our sample size is 25. It is not bigger than 30. So we need to double check that the population is normal. So if you flip back to the problem, they tell us that the distribution of such prices is normal. Okay, and that has to be something that the question tells you. Again, I mentioned in class that deciding whether something is normally distributed or not is something that's beyond the scope of this course. There are other courses where you learn about how to tell whether data is normal. Okay, so I'm just going to have to tell you, if you need normality, just kind of look in the problem and it should be there. All right, so we know that the population is normal, so we don't care how big our sample size is. All right, so now we're ready to plug into the formula. So I plugged in x bar equals 145, z sub 0.9 is 1.645, sigma over root n is 35 over root 25. All right, and I would recommend when you go to your calculator to plug this in, that you do the right-hand side, the stuff after the plus or minus. So type in 1.645 times 35 over root 25, and that should give you 11.515. Okay, so calculating that margin of error is a good first step. Makes things a little easier. So remember that plus or minus is notation for two different numbers, 145 plus 11, 145 minus 11. Okay, I'm going to do the minus first. So 145 minus 11.515, and that gives me 133.485. Then I'm going to add 145 plus 11.515. And that gives me 156.515. All right, and that is our interval for mu. Okay, so we're going to be 90% confident that the true population mean lies somewhere between 133.485 and 156.515. Now, these numbers are referring to prices of books, so I'm going to go ahead and round those numbers off at 2 decimal places, so those make more sense for prices. Okay, so rounding up 0.485 to 0.49 and rounding up 0.515 to 52 cents. Okay, so that's our confidence interval. And with all of our confidence intervals, we're going to translate them into sentences that would make sense to somebody who's not a statistician. All right, so we're going to write the sentence that says, we are 90% confident that the mean price of all such textbooks is between $133.49 and $156.52. Okay. All right, so always a sentence with some units and some explanation for someone who is not currently stuck in a stats class. All right, so that's our first confidence interval. This example asks us a little extra question. Okay, it says, how would our interval change if we are 95% confident or 99% confident? Okay, so here was the interval that we just calculated, and we got those numbers. All right, so the only thing that's going to change, this was a 90% confidence interval. If we want to go from 90% confident to 95% confident, that bit right there is the only thing that's going to change. The population mean, standard deviation, and sample size are all still going to be the same. So we're going to replace that z sub 0.9 with the z sub 0.95. Okay, we calculated that one together and got 1.96. Okay, so we're going to calculate the exact same interval. We just changed our level of confidence. Okay, so when I do 145 minus that number and 145 plus that number, I get this interval. All right. So that would be our confidence interval if they had asked us to be 95% confident. If they had asked us to be 99% confident, we would put z.99 in there. That I just pulled that out of the table that I gave you. We didn't actually calculate that one together. 2.575. Again, all the other pieces of that formula are the same. So if I do 145 minus that stuff, 145 plus that stuff, you get that interval. Okay, so let's just kind of pay attention to what's happening to that interval as we get more and more confident about our interval. All right, so notice the lower values, the left-hand values of those intervals, 133.49, 131, 126, okay? Those numbers are getting lower, and at the same time, the right-hand numbers, 156, 158, 163, those numbers are getting bigger. So like I said earlier, if you want to be more confident that you're actually catching the true population mean, you have to use a wider net. Okay, so the more confident that we get, the wider our interval gets. Okay, and so what level of confidence do you want to pick? Well, that's going to depend on what you're doing. Okay, so if you are just doing prices of textbooks, maybe you want to have a smaller interval because it's okay to be only 90% confident. There's a 10% uncertainty there, and that's okay. And you get this nice, neat, small interval. All right, but if you're talking about doing a drug study where the results of what you do could help or harm people, maybe you want to be more confident. And so you use that wider net and you decide that you could live with the values being spread out more, but you'd be more confident about what you were doing. In a statistics class, you know, your professor is always going to tell you which level of confidence to pick, but it's a little bit more subjective out in the real world when you're doing a study. All right. Okay, so let's do another example of a confidence interval, example 7.1.4. It says, a Texas real estate company wants to assess the average house price in San Antonio. Using city records, they randomly select 50 home addresses and obtained a sample mean of 151.47 thousands of dollars. Okay, so pay attention to what they just did there. That 151.47, they've kind of converted the numbers. Instead of saying $151,470, they wanted to make the numbers smaller. So they just say 151.47 thousands of dollars. Okay, so we'll keep that in mind as we're doing our calculations. So it says construct a 95% confidence interval for the mean cost of all homes in San Antonio. Assume that sigma equals 30 thousands of dollars. All right, so again, we're just going to go through the problem and take notes. All right, so the first number that we're given is 50. Okay, so that is the number of home addresses they randomly selected. So that's going to be our sample size, n equals 50. They give us a number 151.47. They're even kind enough to have used the word sample mean before that. Okay, so that makes it easy to decide that that's an X bar value. All right, and again, down at the bottom, they were really nice, and they even used the symbol for you, sigma equals 30. All right, so you know that that's a population standard deviation. All right, and they want this to be a 95% confidence interval, so we'll keep that in mind when we're choosing our Z value. Okay, so I'm going to take those three values, n, x bar, and sigma, come over to my formula. Our n was 50. Mean house price was $151.47 thousand, and the sigma they gave us was 30. They asked for a 95% confidence interval, so we're going to use z.95, which was 1.96, again from that table of z values. All right. And again, before you do your calculations, you go do your checks. Use this interval only when sigma is known. And again, they used the variable sigma, so you know that's a population standard deviation, so check. The second one, population is normal or n is bigger than or equal to 30. Okay. If you go back and read the problem, they don't say anything about the population being normal, but that's okay because they give us a sample size of 50, which means our n is bigger than or equal to 30. So that means that we can go ahead and use this interval. And again, we're going to talk next time about what to do if you can't check off these two stipulations. Okay. All right, so just plug in all your numbers. 151.47 plus or minus 1.96 times 30 over root 50. Again, I go to my calculator and do just the stuff after the plus or minus, just my margin of error. 1.96 times 30 divided by square root of 50. Okay, and I get 8.32. So 151.47 plus or minus 8.32. All right, again, I do the left-hand side first. 151.47 minus 8.32. Okay, I went ahead and rounded that off at a whole number. Remember that these represent thousands of dollars for house prices. So I just rounded that to $143,000 for a house price. I thought that might be easier for us. All right, then we do 151.47 plus 8.32, rounded off to a whole number, I got 160. All right, so our true mean population house price in San Antonio is between $143,000 and $160,000. All right, and again, once you have your interval, go ahead and write a sentence that would make sense to somebody who doesn't know anything about statistics. We are 95% confident that the mean home price in San Antonio is between $143,000 and $160,000. Okay. And like last time, they kind of add on an extra bit on the end of this one. They ask us, how would our interval change if the sample size was 100 or 500? So remember that our sample size was 50. Here was our calculation, 151.47 plus or minus 1.96 times 30 over root 50, and we got 143,000 to 160,000. So now they're just asking us to change the sample size. So they still want us to be 95% confident, but they want to say, what if we had gone out and got this data from 100 houses instead of just 50? All right, so all I did was to replace that square root of 50 with a square root of 100. Okay, so if I do that calculation in my calculator, do the subtraction, do the addition, you would get 146 to 157. All right, and then let's do it again for 500. Okay, so again, I copied exactly the same numbers, just replacing that 100 with a 500. Okay, and if you do that, your low bound is 149 and your upper bound is 154. All right, so kind of studying what happens as our sample size goes up. In the last example, we found that when our confidence goes up, the interval got wider and wider. Here, when our sample size goes up, the intervals are getting skinnier and skinnier, right? Our original one went from 143 to 160. Okay, so that was a large width. But then when we got 100 homes in our sample, it went into 146 to 157. So we kind of lopped off $3,000 off each end of that interval. And then when we went up to 500, we lost another $3,000 off of each end of the interval. So we kind of honed in. Now we're between $149,000 and $154,000 for that house price. Okay, and the reason why, when you get more information in your sample, a larger sample size, you can be more easily confident about your interval. You've got more information from the population, getting 10 times as many houses, going from 50 houses to 500. Okay, so it makes sense that you can kind of zero in a little bit more on your point estimate there in the middle. Okay, so when the confidence value goes up, the interval gets wider. So now we know that maybe we can compensate for that by also picking a bigger sample size. Okay, so if you really need a high level of confidence, it makes sense to try and get a bigger sample so that you can kind of counteract the width of the interval getting too big with a high level of confidence. All right. Okay. All right, so that was it for that section 7.1. Again, don't forget to do your homework. You can turn it in on Monday when I see you, and I hope you guys have a wonderful weekend.